session is by Professor Vinjanampathy, and I think we're going to go to the movies part of this talk.
Yes.
Quantum synchronization in the quantum regime.
Yes. So thank you very much to the organizers for having me here. I'm super excited. This is the first time that I've been at RRI, so I'm very excited to be here. So today, essentially, I'll talk to you about quantum synchronization in the quantum regime. So this is joint work with Samir, who's an undergrad at IIT Bombay, Mikhal, and Manas and Kwek, who are at CQT, Sarufazio, who's at ICTP and SNS PISA, and Vlatko, who's at Oxford, and several have visiting positions. So let me get right to the story, but I'm very susceptible to suggestions. So when Lorenzo started his talk, I quickly added this slide in because then you will remember my slides. So, so this is the outline of my talk. So because this is essentially combining two ideas, one in classical mechanics and trying to move it to the quantum regime. This was new to me before I started, and I presume that at least some of the audience is going to be new to. So I'm essentially going to spend a lot of time just setting up the problem and kind of talking about the classical mechanical version of it, and then I'll get into the quantum stuff, and we can move on from there. So, so hopefully that's the. So let me introduce you to quantum synchronization. So so this. I thought it's better to just show you the movie than to talk about it. So synchronization is essentially behavior that was first discovered by Huygens, and so you can see what it is here. So there are two essentially oscillators that bring their own energy. So they're self-sustained oscillators, and they're coupled weakly by the fact that they're sitting on a platform and there's what looks like two Coke cans. So this is just a movie from YouTube. And there are several such demonstrations, and they illustrate the point essentially, which is that if the conditions are right, and you have to kind of set those conditions down, then these two oscillators essentially can synchronize in phase. So they start moving together with each other. And the famous London Millennium Bridge incident is actually related to this, as perhaps some of you know. Control L, right? Yes, there we go. So, so if you look at a classic textbook on synchronization, like Pekovsky, it says we understand synchronization as the adjustment of rhythms, right, of oscillating objects due to weak interactions, right? So this is essentially what I want you to hang on to. And why are we interested in synchronization? Well, this is a kind of quite a mature field in nonlinear dynamics, essentially because it has ubiquitous, it's all over nature essentially and over artificial systems. So networks exhibit synchronization, fireflies exhibit synchronization, circadian rhythm, heart, so on and so forth, right? So there's all kinds of places where you see this in the classical world, and which has caused a tremendous amount of research in this area. In this talk, essentially, I'm going to talk about a simplified version of synchronization, which is essentially going to be semi-classical. So synchronization, as I've just explained to you, is two oscillators, and they go in phase essentially if the conditions are right. But actually, what I'm going to do is I'm going to take one of those oscillators away and replace it with a reference, classical reference, essentially just an external driving. So this is this is exactly what we do when we do essentially semi-classical treatment of light, right, on an atom. So you replace one of the systems that you're interested in with a classical object, and then you study the interaction between the classical and the quantum, right? And so I want you to imagine, forget about the qubits, this was drawn in a different context, but what I want you to imagine is some sort of object which may or may not be quantum or classical, and it's being essentially forced from outside. An external oscillator is forcing it from outside, and you just want to lock on the frequency, right? And that's the essential idea here. So what I want to tell you about, when I talk about synchronization, there are several prototypical examples, and so the one that we'll be focused on is essentially called the Van der Pol oscillator. So, and I just want to take a second to set up the Van der Pol oscillator so that you can share with me the intuition that I have. So just consider this differential equation for a second, and in fact set all the kind of distracting terms to 0. So let's just set mu to 0 and f to 0. right? That's a good old harmonic oscillator, and I know what that looks like, right? So that looks essentially like that red line right there, right? And so what happens is that if you now essentially have, if you now switch on mu, and forget about f for a second, if you switch on mu, what happens is, and you imagine that the oscillations are strong, right? So they're larger than 1. Then what you have is a damping effect on the oscillations, right? And likewise, if x is less than 1, then this term is positive, and then you have a pumping effect on the oscillation. So if the conditions are right, then what you can do essentially is you can set up a dynamics like this, a classical dynamics like this, where essentially you could have some stability in the which is coming out of cancellation of energies. Essentially, that's the way to think about it simply. So you can draw the phase diagram, and there are fixed points and limit cycles and so on and so forth in this. And this is just the kind of very canonical example of what a VDP limit cycle looks like. So as you increase the damping parameters given there, right? So, but one thing I just want to emphasize essentially, is that these oscillators essentially have to obey a certain set of conditions for them to be synchronization, for them to be considered a problem in synchronization. And being a little loose on this issue has actually caused some bit of confusion in the literature, because if I consider two harmonic oscillators and I just nail them together, right? I just take a wooden board and I just nail them to each other. Well, of course they oscillate in phase, but there's nothing exciting about it. Right? We're not terribly worried or excited about this. So what you essentially want you want to have the coupling to be weak, so that it's surprising when they do synchronize, that there is something exciting happening on top of the typical dynamics that you expect. And the other thing is you want some sort of nonlinearity, and I feel like I want to justify the nonlinearity to you. And so on some random parametric axis, I'm just plotting the energy. So imagine that there is a straight line which essentially indicates either linear growth in energy or a linear drop in energy. And if you have something that's nonlinear, then you have the possibility of intersecting this. Right? Of course, you could get the sign wrong and you could flip the other way, and then you wouldn't intersect it at all. But you could intersect, if you intersect this, then if one of these lines represents pumping and the other one represents damping, then there is an energy cancellation that is possible, which essentially stabilizes the system. And that's essentially another way of saying everything that I've just been saying just now, right? So those are the essential ingredients that we need, even in the classical universe, to discuss the van der Pol oscillator, right? So here is just two more things I have to introduce to you, and this is, you have to carry these with you into the quantum world. And this is that I can replace, one of these is very simple. I can replace the second order differential equation with a complex first order differential equation. There is some averaging techniques that you have to go through here, but essentially that's it. It's just that you can replace the second order differential equation with the first order differential equation. I think I forgot to add the forcing term here. And I've written it essentially in a slightly, this equation has a mu and an f, whereas this equation doesn't have a mu and an f. And it's essentially because I've just replaced one mu with two mu's, so I've just called them gamma 1 and gamma 2, just so that it looks correct when we go into the quantum regime. So this equation is essentially this equation, and you just have to buy that for now. Please grant me that. And the other is essentially this idea of what happens when you try and synchronize two oscillators, right? So, or in this case, when you try and entrain essentially an oscillator to an external frequency. So what happens is the following. So a diagram like this is very typical, which is, so imagine that your driving frequency with reference to the natural frequency of the oscillator, if it's on resonance, then of course it'll synchronize, right? So this is a trivial synchronization, but as the driving frequency starts drifting from the natural frequency, there is a given region where you would expect, if these objects are to synchronize, that you would expect that these things will synchronize. So you expect essentially that the difference between the observed frequency and the drive frequency would be 0 for a while, right? But if you take essentially something that's a megahertz oscillator and you drive it at gigahertz, right? That's too much of a frequency difference for it to be able to kind of lock on, right? There's so much energy, there's so much frequency difference that it's just going to stop, listening to the drive, and it's just going to go back to its natural oscillation, right? So what you expect even in the classical setting is essentially a diagram like this, where the difference frequency is flat, and that flat region essentially indicates synchronization. right? And then it essentially just uncouples from the drive and just goes back to its natural frequency. And so that natural frequency is just drawn on that line, right? So you'll see diagrams like this, and so I want you to understand what the physics of the diagram is. Now, of course, this is drawn at a given strength of driving, right? Now, as I drive harder and harder, I would expect that I can get it to synchronize for a longer and longer time, right? Because amplitude also plays a role in transferring energy onto this system. So, but again, the same argument applies, which is that beyond a point, nothing's going to help, right? So what you see on this axis is essentially this diagram, several of these diagrams drawn with larger and larger forcing amplitudes, right? And so you get this tongue-like behavior, and this thing is called the Arnold tongue, right? And so I'm going to show you diagrams, pictures of the Arnold tongue for quantum systems, so I just want you to understand what the physical content of those are, right? So inside this region, we have synchronization. Outside, the system is essentially unresponsive and just goes back to its natural frequency, right? Slowly. So these tails are supposed to indicate that, right? Good. So then the natural question that perhaps all of us have in this room is why quantize? Why bother with all of this, right? And the why bother question is essentially both easy to answer and difficult to answer, because it's easy to answer because we can, right? It's interesting. It's both kind of one half fundamentals, one half foundation, frontiers. The other reason is because it shows up all over the place in the classical universe, of course, but here is an example of a phonon laser that's being discussed in the Valhalla group. And if you just look at the dynamics, it's essentially a VDP. So there seems to be some very, very interesting reasons that we would want to pursue VDPs in the quantum regime, because they seem to give us a lot back in terms of physics. The other reason that I think is a bit far-fetched, but perhaps I can say it with a pinch of salt, is all of us are imagining the quantum internet, right? And I believe Peter is going to talk about it in the afternoon today. And the quantum internet, essentially what we are really trying to discuss is the collective behavior of many, many subsystems that are all quantum at some level, right? And we know what happens when we start discussing this kind of physics, right? So there's all kinds of very interesting stuff like decay superradiance that's waiting for us. And so combining that with the nonlinear dynamics that our friends in the other communities already know would be great, I mean, essentially. And so that alone is, I think, inspiration for us to go down this road. So, okay, so here is the introduction to the quantum version of the VDP, right? And this is due to Professor Bruder's group in Basel, it's a PRL from 2014. I'll keep referring to this as the WNB paper. So here what they suggested was the following, which is, they said, consider this Lindblad equation that's written essentially in the rotating frame, right? So and so this delta is the detuning between the natural frequency and the driven frequency. So that detuning is exactly what this delta represents. The F is the force term. So this is the external oscillator being the external forcing that's coming through into the oscillator. And there are two dissipators, and you can recognize that one of them is a linear pump and the other one's a nonlinear damp. So physically, like if you just squint for a second, this seems to have all the features that we're interested in, right? It has the nonlinearity, it has all of the physics that we're interested in. And so you can go ahead essentially and just compute the expectation value of the annihilation operator, and the equation is exactly the equation that I showed you before, right? And that was the reason that I cheated a little bit and showed you the equation in the correct form, essentially because this follows essentially from the calculation. So what they essentially said was, they said, okay, now you have this, and you can discuss either the classical dynamics of this object, or you can discuss the quantum dynamics of the quantum system, because we have the quantum system in our hands. So what we can do is we can take this density matrix evolution equation and we can evolve it essentially to steady state, and we can stare at what the Wigner function looks like, right? And so what you see here are essentially the overlays of the classical dynamics and the quantum dynamics, one on top of each other. And what you see is essentially that the classical dynamics in the unsynchronized regime, so I've just shown you two figures from the PRL, one of which represents the unsynchronized behavior. So in phase space, essentially this thing is all over the place because it can't pick a phase. Whereas in the other regime where it is synchronizing, and you can see the classical trajectory over there, the quantum trajectory is essentially smeared out on top of it, right? And the smearing is just the uncertainty principle, right? And this will start playing a strong role essentially in a couple of minutes. So this is the first step essentially towards quantum synchronization. And there was a kind of quite a close paper from Sadehpur's group that came out right at that time. And so, okay, so now what do we have? These things, these D of A dagger, I'm sorry, I should have written them somewhere, are just standard Lindbladians, right? And so this is just the standard textbook notation for Lindblad operators. So these are just the Lindbladians, and they come with two rates, gamma 1 and gamma 2, right? And so now you can discuss two regimes of physics, essentially. Again, let me emphasize that we're interested in the steady states of the physics. The first regime that you can emphasize is essentially when gamma 2 dominates over gamma 1. Gamma 2, if you just read it off, is the damping term. So the damping dominates over the driving, over the pumping, and so everything is near the ground state, right? Whatever energy that you try and put into the system, it just gets sucked out by A squared, right? By the A square bath, by the damping bath. On the other hand, you can also imagine a regime where gamma 1 dominates, and you essentially have some steady states which are highly populated steady states, and you get much closer to the classical behavior, right? You can think of it as action over h bar, essentially, and that physics is dominated over in this region, right? And essentially all I'm going to talk to you about, my work, our work, is essentially about going from here to here, right? In a way that I'll explain to you as we go along. So before I do that, what I wanted to show you, just as a kind of a general introduction to this new area, this emerging area, are the different kind of ways of measuring synchronization, right? You can say, look, okay, this is all fine, but you have to give me proof. You have to give me proof that this is synchronization, and you have to give me proof that this is quantum synchronization. There's something interesting happening in the quantum regime. And so there have been several suggestions that have come up, and I just want to share a couple of them with you just to give you a flavor and perhaps even to get you excited in the field. And so the first one is based off of uncertainty principles. So you can essentially say, well, I imagine that I have a vector which essentially is rotating in phase space. And so if I have two vectors that are rotating, essentially the x and p differences essentially tell me the quality of synchronization. So if the x and p have locked onto each other and they're going in phase with each other, then this is a very good synchronization, otherwise it's not. So you could define essentially a difference of position and difference of momentum operators and build a measure of synchronization off of that, which has been done. Likewise, you can actually say, well, you know, what are we interested in? We're interested in trying to take this classical mechanical effect, which I just showed you, and move it into the quantum regime so that we can actually have fun with it in the quantum regime. So what you want is you're interested in a measure that actually survives through the quantum classical transition, right? So if you, for instance, some of the early suggestions had to do with entanglement, right? If you take a couple quantum systems which are entangled and essentially just increase the total action over h bar, then you essentially get into a classical regime. And where is the measure of synchronization then? So the suggestion was essentially that perhaps we should look at mutual information, right? And mutual information does indeed survive both the classical and the quantum. And this paper demonstrates essentially for a variety of situations that if you want to measure synchronization, then it does survive, right? And the reason that I showed you essentially the Arnold tongue is because you can see it essentially in this and the next one that I'm going to. But Karthik, you had a quick question? In the classical regime, this entire thing is going as 1 over h bar. So in the classical regime, the thing goes off to infinity, and it's unbounded. Yeah. So the whole thing is in this. Yeah. So yeah, it's a very nice paper. I recommend it. Right. And so the other thing that I also wanted to show you, because I know there are many experts in Discord in the audience, is that for a while essentially Discord was also discussed as and I think it's still in the running, and we have to see how any of these measures, what they teach us about the underlying synchronization. So so this is all I'll say about that. Okay, so what's the problem, right? This is all the review part of the talk. So hopefully you're a little bit with me with respect to what we are trying to do. So what is the problem really? The problem is the following. So if you look at Bruder's paper, if you go back to WNB, what they did was they plotted the power spectrum, right? And which I've just defined just for convenience here. And what they see is they see the following, which is that these sharp lines are essentially just the classical synchronization. The solid lines are classical synchronization. What that means is when you synchronize, and all of the power is emitted in the shifted frequency, right? So which is you've managed to move the oscillator onto the shifted frequency. But when you don't synchronize, you don't synchronize. The thing just goes back to its natural frequency, right? But if you look at the quantum synchronization, so here is two examples. One is with weak driving. So the only thing that I want you to take away, I know these plots are busy and I apologize for that. The only thing I want you to take away is essentially that this is weaker than this. 0.5 is smaller than 0.7, so the red is weaker than blue. And so when you have weak driving, essentially you don't have synchronization. The quantum system fails to synchronize and the classical system does indeed synchronize, right? So what's happening is something funny is happening. In the quantum regime, there is something that is spoiling the synchronization that's coming in and spoiling the synchronization from happening for weak values of driving. But if you push on the drive, then what you get into is this regime, which is in blue, where indeed it does synchronize, right? The other thing I want you to notice is that the power spectrum is actually super broad in the quantum case, right? Both of these are actually worrisome, and this indeed is the problem. So this is the opportunity, if you want to put it that way. And so we try and resolve this issue essentially in the quantum regime, and this is what I want to show you, right? So just before I show you the solution, so here is again from the same paper, they make the exact same point by essentially showing you in the weak driving and strong driving regimes the Arnold tongue, right? So this thing where you synchronize for a while, when you're flat, it's good. And then when you uncouple and go off towards the diagonal, then you aren't responding to the physics, to the external drive anymore. And what you can see is that the quantum is completely on the almost on the straight line, right? If you look at the inset, then there is some amount of synchronization there. But essentially, this thing is very bad. I mean, that's essentially the point that you have to take away. And even here, the quantum is weaker than the classical. And so, you know, Bruder, the authors themselves essentially say that, look, it's the uncertainty principle. It's the fact that you have all this noise sitting here that's actually messing with you. It's not allowing you to synchronize because, you know, it can't. The noise is overwhelming essentially any drive that's coming in, and then they say, well, okay. So that's their commentary on this. So we thought, okay, we should try and resolve this, and you know, we of course want a phase standard, right? I mean, so this was a very naive way in which we approach this entire thing. We said, you want to lock onto a phase. The phase is being spoiled by noise. Well, okay, I know exactly what to do. Essentially, squeeze on the appropriate quadrature and then rotate so that you essentially have maximal sensitivity in that, you know, to that phase, and that will get you out of the problem. Right? It turns out that for reasons that we're still trying to understand, we're only partially right. In that, yes, squeezing does help, but you know, it helps better than we expected, essentially. So what we did was we just took the exact same model that Bruder had, and we just added essentially a squeezing term to it, right? And so when we look, so let me show you again what we found in pictures. So this is the power spectrum essentially, and the Arnold tongue. You can barely even tell. So, and this is with harmonic driving. So this is the standard driving that Bruder had in their paper. And what you see essentially is that well, this thing is entraining, but essentially as you increase the drive, the power spectrum is becoming flatter and broader. So it's broadening out essentially, which means that if you estimate the full width at half maxima, right? If you call it sigma, the sigma is deteriorating essentially in the harmonic drive, right? And so this is not a very good synchronization, because if you want to imagine, you know, let's imagine the kind of most fantastical application of this, that you want to do some sort of clock synchronization with it or something like that. You can't even find the peak of the power spectrum. So you know, if you were to make an experimental proposal and they looked at this particular diagram, this would be disheartening essentially from that point of view. So what we did was we analyzed this with our squeezing drive, and what ends up happening is that the power spectrum actually becomes much sharper, and it entrains much better, right? Now we're comparing apples and oranges, because you know 0.75 on a 2-photon, like on a squeezing drive, is not the same as 0.75 on a harmonic drive, but nonetheless, I mean, I leave this diagram for your interpretation, and you can also see essentially that the entrainment is much better, you know. Even here, right? And so the last thing that we wanted to check was so let me reiterate what we're trying to resolve. We're trying to essentially observe quantum synchronization in the quantum regime, very close to the ground state. It's being spoiled by noise, yeah.
Sorry, can you just say what is squeezed? Is it the driving signal that's squeezed, or where's the
so we add another signal essentially. So this is not just the driving, but we add another signal on top of it, which is just
on top of the driving?
On top of the driving, yeah. And we actually even switch off the driving afterwards. I mean, the driving, so if you, in the paper, we essentially point out that the driving is not required. You can just switch it off completely and just do the entire thing as squeezing, right? So, okay. So this is this achieves, we believe this achieves what we were trying to get to, which is it essentially sharpens the power spectrum, and it's quite nice. We wanted to ask, is this actually quantum light, right? Because after all, we want to see quantum, right? So is this quantum? So we essentially calculated the Mandel Q parameter, and indeed you can see essentially. So this is a very busy graph. I'll just take you through it quickly. There are only essentially 2 or 3 interesting things that I want you to see here. So this is the full width at half maximum, and you can see for the harmonic drive it increases, right? Even though the Mandel Q, which is in orange here, is always negative. So harmonic drive is good, it produces quantum stuff, but essentially the quality of synchronization is bad, and it's indicated here by the fact that the full width at half maximum is just going off, right? It's taking off. Whereas for us, essentially, the Mandel Q parameter is negative in this region, but then since then we've computed squeezing and other parameters of quantumness, and they register all over the place. And so all this stuff is quantum, but the Mandel Q only points this out. So here essentially we do indeed see a reduction in the full width at half maxima, which is exactly what we want, so that the peak of the power spectrum stands out and we can actually see this. So this is essentially the point that we wanted to make. So what we did, the very last thing I just want to say in a couple of minutes is we also analyzed what the phase space dynamics looks like, because again we want to bring, we want to have a conversation between classical and quantum. So we said, okay, let's look at the classical phase space trajectory. So what this is it's just the amplitude and phase of the beta that I just showed you, the beta equation that I just showed you. It's that equation in terms of amplitude and phase, and for in the classical regime, so that this actually makes sense as a classical dynamical system. And so if you just look for fixed points, essentially what you can see is the emergence of a bifurcation, right? So you can see this black as the fixed point, and as you essentially you can move it around, but you can essentially, when you increase the squeeze, you develop essentially a bifurcation, right? And the bifurcation is symmetric, but it can be made asymmetric essentially by playing around with the detuning, right? So this is what we observed in the classical regime. So then what we did was we said, okay, does the quantum system show the signature? So we went deep into the quantum regime again, so the one where the damping is much stronger, and we plotted the Wigner functions. And lo and behold, it does exactly the same thing. So essentially, so when the detuning is switched off, it has the symmetric bifurcation of the Wigner function, whereas when you switch on the detuning, it picks one or the other branch completely exactly like the classical dynamics underneath does. Right? So this is very exciting because we somehow are we have a prototype essentially which plays both with classical and quantum mechanics at the same time, and I think just that is an exciting, perhaps an exciting thing. I'm very excited by this. So there is also some suggestion on how to experimentally implement this. Sadehpur's original paper essentially suggests a 2-photon drive with a strongly damped electronic state, and we want to combine it with some suggestions from Wineland. So we've been thinking in ions essentially because one of our co-authors, Manas, is an ion trapper in the ion trap language, and so we want to combine it with some suggestion from Wineland on essentially trying to implement a squeezing drive directly. But this is essentially with preliminary work. But I just want to point out that we do have some ideas of how to do it, and even to bypass some of the issues, the initial issues that are here. So let me summarize. I'm right at 27 minutes. So squeezing, I think, actually enhances quantum synchronization. So I think it's a great, so hopefully we've combined these two ideas of VDP and squeezing. And so it shows all of these things that I just mentioned. So they produce genuinely non-classical states. Their full width at half maxima is actually goes down, and the power spectrum gets sharper. So we hope that actually, that this is implemented so that we can see synchronization, essentially entrainment in the quantum regime, realistically. So thank you. I'll take your questions. And so here is the paper.
So we have some questions during the talk, but I think maybe 2 or 3 minutes,
yes,
which we can have for more.
It's
from the audience.
It's a competition between your curiosity and your hunger. So, because I stand between you and lunch.
So in the absence of squeezing, you showed that the power spectrum for the quantum case is broad, the steady power spectrum. in the absence of squeezing. For the harmonic trap, in the absence of squeezing.
Yes.
So now, suppose, I mean, the steady power spectra may be broad, but the time taken to go from, suppose, the worst case possible where the two oscillators are completely out of phase to the steady state, the time limit that is taken, so maybe there is some trade-off between, I mean, whether, if the time taken is less, then the synchronization may be also less, or vice versa. I mean, is there any trade-off involved in that?
I don't know, because we only analyze the steady states, but let me just point out one thing quickly. All of these diagrams are essentially in the steady state, right? So you start off, I mean, so the imagination is that you switch on all of these lasers and you forget about it and just wait. And hopefully the entire thing synchronizes, right? So, I think if I understand your question right, it's about the speed with which you get to this thing, which I don't know whether that is particularly relevant at zero order. I have to think, maybe this is interesting. But what I want to tell you is that if the power spectrum is broad, it actually means that the frequencies that you're recording as to how it's oscillating is varied. You're getting all kinds of, and that distribution is bad. I mean, this is a worse problem essentially. And so, so that's that's my first thought on that. Yeah. Yeah, please.
Squeezing parameter choice that you have?
It's just arbitrary units because we didn't put in. Yeah. So that's squeezing right there directly. Yeah, that's squeezing. That eta goes directly into the squeezing. So yeah, it's right there. Yes, exactly. Right. And the point is that we were actually when we started, we anticipated that we'll have to tune so you can do the classical dynamics and you expect essentially, let's say in phase space, you expect the classical dynamics to lock here, right? So we expected essentially that we'll have to tune on to that quadrature and essentially squeeze so that you get better phase access. Completely irrelevant. Don't know why. The power spectrum doesn't care. Yeah.
It just looks like some kind of a control that you have with your squeezing.
Exactly.
Without knowing what, that is without having a full control, you are introducing some control. Yeah. So if you analyze it with some filtering theory, where you might be able to see if the steady state is reached earlier or later with this in a neater analysis.
So, so the time for, time for thermalization, as you probably already know, is a very difficult problem. So I can numerically, of course, estimate.
But in simple cases, it can be understood with what kind of tuning that you are doing with your driving field.
Yeah. Actually, I mean, it's an interesting point because even the classical dynamics, you could start it at the same and see whether you should be able to evaluate things. So perhaps entirely.
Well, let's thank the speaker.
Okay, thank you.